So you have to go very fast, so that to cover all these things. So anyway, welcome back. Good evening, everyone. So now in this session, I'm going to talk about the soil ground improvement by drainage, different dewatering methods or technique, and then consolidation of soft-soil. I don't know whether I should cover this because everyone knows, but I may go quickly. And then the foundation treatment method for soft soil by using surcharge or PVD, surcharge or preloading. And then we will talk about the vertical drain. One is the sand drain, one is the PVD, the prefabricated vertical drain, and then also talk about the vacuum consolidation. So there are, I have to go really quick to complete all this. So now, as I mentioned, it is get rid of the water, right? So dewatering technique. So first thing is, what is the effect, the detrimental effect of water? Okay, in geotechnical engineering, it reduces the soil shear strength and stiffness. Okay, increase the soil weight. Sometimes increase because the soil is saturated. Unit weight is increased. Generation of excess water pressure, that you don't want that. So for any infrastructure, so anything is the pore pressure, again, you have to go to the soil mechanics, that the pore pressure increase means the effective stress decrease, and then it's not good. Necessary conditions for liquefaction, development of uplift process, sometimes the water will give you uplift pressure, that is not good. Increase of lateral earth pressure. So again, that's why, for back lateral earth pressure design, we use granular type of soil, all the water drained out quickly. If the water is there, the water will give you additional load. Soil expansion happens, expansive soil or soil collapse. And then erosion of the soil particles takes place, and then also freeze and thaw, because the water is the one. If there is no water, there will be no freeze thaw, So so now thing is, water you cannot control with the rainfall, water table, so we don't have much control. So then what are the different methods to control the groundwater? One is the drainage, and then we just drain the water. And then obviously we need to use different type of pumps and well, and then depending on the parameter of the soil, you need to check. There are different dewatering techniques we are going to talk, and then also the barrier system. We just really cut up the water, okay, by using different things. So it may be sheet pile, it may be the bentonite barriers, all these things. But then again, we are not going to talk about that over here. So just for example, as I mentioned, there are three examples. One is the drainage. So again, mostly the retaining walls, we put a drainage filter over there, and then using just like a coarse grain gravel there, and then also they put a geotextiles on the top layer, and there is a pipe. So that's how we just the drainage only, so that on the retaining wall, all the drain water will go. Dewatering, again, using some type of pump to get rid of the water. So if you want to construct in dry situations, so construction in dry situations, you have to just pump the water out to the original water tables, and go down, and then you can do your construction in dry situation. And then the barriers. Sometimes we need barriers, so we are not going to go in details over here. Just for example, some pavement generally fell because the water table fluctuation. There is a drainage is not proper. Sometimes we do some barriers so that the water really cannot go up, and then they create a problem to the pavement. Okay? So these are like a well point system, watertight barriers. So these are things I'm going to go in much more details now. So now the thing is, why we need that the groundwater so how to control the groundwater while the excavation at the excavation site. So groundwater is usually regarded as one of the most difficult problem in excavation work. And then also to remove the water, so we need heavy and continuous pumping, and that is expensive. So it may, and also when you drain out the water, sometimes the surrounding structure may subside or settlement. And then also the process, the removal of this excess water from the saturated soil mass is known as the drainage. So this is called the drainage or dewatering. So we'll go more detail what are the different the dewatering method. The process helps us increasing the stability of the in situ soil mass by reducing the seepage and the pore pressure. So the various civil engineering construction, sometimes we need the excavation need below the water table, and these are the special situation while you excavate the basement of a building or lying foundation of a dam or bridge or excavating a drain, with the water, we encounter water table. So we need to remove the water, we need to drain the water so that the water table is going down, and then or for laying sewer lines, okay? So all these situations, all such excavations do require lowering of groundwater or water table below the bottom of the excavation. So now, how to do that? There are different methods to do, okay? So the dewatering or control is obviously the groundwater can be defined as the water held temporarily in the water soil above the water table, the groundwater. Dewatering is a process to lower down the water table reasonably dry working conditions, especially for the excavation activities. So that can be temporary, it can be permanent. So most of the cases, the temporary is exclusion of water table by lowering down the water table. Permanent, generally we do the cutoff wall or the flow of groundwater. Most of the cases use environmental applications. We use that slurry trenches. So purpose of dewatering is basically, you do the construction when its water table is really up. So we need to remove the water table so that you can construction can be in dry situation. The permanent dewatering system are far less commonly used for temporary or construction dewatering system. Most of the time, you just temporary, and then when the construction is done, it's fine. The structures is done. There's no problem. The common dewatering methods or dewatering techniques is basically this again, everyone knows this, various methods of dewatering groundwater: pumping from the open sump, pumping from oil point, pumping from bore wells, pumping from deep wells, and then also pumping from horizontal wells, and electro-osmotic method to lower the water table. So again, what method you're going to use, that depends on the site conditions, what type of soil is there, what is the permeability of the soil at the site. So that is very important. And then also the extent of groundwater depends on the subsurface stratification. That is important, very important. Presence of water-bearing strata, where is the water table located? Aquifer permeameter or in situ permeability. So that's, again, while doing this well bore, so we need to know what type of the confined aquifer, unconfined aquifer, all these things you need to know, or parched aquifer. So this is like a open sump, pumping from open sump. So you just make a hole, and then so obviously the water will go. So obviously the water will from higher depth to lower depth. It will go, and then it will just deposit it there, and use pump to remove the water. Okay. So obviously you see our initial water table was here, and the final water table is going over here. And obviously when doing this, the sump pump, and then you need to have some filter type of design, so that otherwise you'll be pumping clay with salt. So we want only pure clay. So that's why in the figure over here you see the gravel. So that will just only the water will you can pump. Then advantage of this method, open sump, you can not more than 8 meters below the pump. Okay, that is the limitation of this. So, and when you can use this, when the site area is large enough to permit excavation and cutback is stable slopes, it is easy. And there is no important structures close to the excavation. It might damage the settlement resulting from the erosion and due to the water flowing towards the south. So that is important. So again, this is very easy method, but the limitation is if you want to reduce the water table below 8 meters, it's not possible. As I mentioned, is the filter design. So we're not going to go in detail. So most of the time we use like a granular type of filter. There are geotextiles filter. So you need to design that. So in the wall, so basically when you need to put that, most of the granular filter, so that when you pump the water, you just pump only water only. Okay, I'm not going to discuss in detail over here. And then also the filter design. So I'm not going to go. So then the second one is pumping from well point. So what you do, you just make a borehole and then pump the water out. So what is going to happen? Obviously, there are, you see the standpipes over here. These are the observation boreholes. And then you see the original water level was here. And now it will forming an inverted cone, okay? And then obviously, so how much is the distance from this inverted cone? So that will be the radius of influence. How much is the radius of influence for one borehole? So beyond that point, there will be no reduction in the groundwater table. So here, well point. So depending on the area, you need to choose how many number of well point you need to use and what type of pump you need to use. A lot of things in design problems. So, but this is very basic things. Sometimes you need to use the multiple lines of storage well points required for extended more than 4 to 5 meters below the groundwater table. Okay. So then this is how it looks like. So there is a header pipe over here. There is a riser pipe, and there is a well point is here. So basically, this is just only one, and all there may be several of that well points that will be connected to the header pipe, and then the header pipe is connected to the pump, and all the water will be removed from there. This is a single stage well point system, how it looks like. Then again, how to calculate how much is the water is coming out from the well. Again, everyone knows how to calculate that using the Dupit-Thiem's approximation. So again, QWQ, this is the equation for unconfined aquifer. There are unconfined aquifer, confined aquifer, and sometimes you need to, this is for the well is penetrated up to the full depth. And there may be equation for the partial penetration. I'm not going to explain that over here. Most of the time, you will use that the equation for full penetration in unconfined or confined. The equation you can find out. So the total, the quantity of water, again, it based on that Darcy's law. Easily you can find out that Q is equal to Ki, how much of the water is going to be coming out. So, so over here, the K is the most important, the permeability of the soil, surrounding soil. And so the equation, the first part is, this is ln, so obviously the log base E. So if you want to use log 10, that there will be factor 2.303 factors, you need to use it in front of that, the equation. So this is for unconfined layer. This is for the confined layer, how to find out for the single well, how to find out the discharge. So this is a standard equation you can calculate. So basically, you need to know how much is the diameter of well, how much is the the distance from the influence, how much is the influence radius, influence zone. After that, there is no water table reduction. So you need to know all this, and easily you can calculate. So the drawdown curve, how it looks like. So over here, the one side well points is the one coil. Initially, you see the water table was here. Now, because of this well, so now the drawdown curve, this looks like, that the inverted cone, as I mentioned, the final drawdown curve is there. So basically, if you want to do excavation, so do something, construction at this point, you can easily do it. So this is like a two-sided well points, how it looks like. It's a similar symmetrical structures. This is the water table is finally below. So initially water table was here, now the water table is here. Okay. So you can do this part, the construction over here up to that depth in dry situation. So there are a few things you need to know about the well point system. So the groundwater installation of this, the filter well, number of filter wells usually 1.5 to 1 meter long, 5 to 10 centimeter diameter. Okay, and the vertical riser pipe is connected to the header main. And here in this cases, the water can be lowering water 5 to 5 meter below the level, generally regarded practical limit. That is the maximum limit you can go. The well point generally is spaced between the 1 meter to 1 meter to 2 meter. And if it is more than 6, you want to remove the water level more than 6 meter, then you need to use not only the single points, you need to use multiple points. Okay. And then if you want to do the reduction or lower the water table more than 16 meter, then you have to use the deep well system. So there are single method, single well point, multiple stage well point. If you want to go deeper, then use a deep well system. This is like a well point system, how it looks like. This is a well point, and there is a, as I mentioned, the header pipe and the riser pipes. There may be several riser pipe will be there, and then for multiple system, and then how much is the original water table, and now after the dewatering technique. So this is the water table, is the final water table. So this is deep well system. Again, deep well system generally uses submersible pump, and there is a PVC casing, and then you need to, and then on the top there is a bentonite seal, and there is a riser pipe, and then the header pipe should be connected. It's the same concept, but only thing is a submersible pump will there, and that can pump because it's really deep at depth. Okay. So pumps are placed at the bottom of the well, and they are more powerful than the well points. It requires wide spacing and fewer well salts because it's a deep one. And they're used alone or in combination of the well points. So this can be used in the deep combinations, and it can be just the pump on the top and then well. So these are the few things I just want to mention over here in deep. So there are you can use the chart or nomogram for the well point spacing. So you can from the groundwater. So you need to know how much is the groundwater reduction you need. And the second column is, you see there is a spacing of well points. And the last column, you see what type of soil. So depending on what type of soil you are working on, whether it is uniform sand and gravel, this chart is for the clean uniform sand and gravel. And then you want to know how much is the lowering of water table you need, and just draw a line, and you can easily calculate how much is the spacing required. So this graph is nomograph of uniform clean sand and gravel. And then there are nomograph also for non-heterogeneous sand and gravel. So maybe in the tutorial today, I'm going to solve one problem using this graph, a chart. Single well point system. So as I mentioned, this is the maximum. It can go up to 5.5 meter. And, so, and then if it's a single point, if you can do the multiple stage, so you can do how the water table can be reduced. So initial water table was here, and then the final water table is here, is quite low. So you can do the construction in dry condition. So sometimes, as I mentioned, so you can use the well point and also the deep well together. Okay, so the well point, because the capacity is less, so you can use 3. So you can do just only the deep well, only 1, and then the water table can be reductions is a greater extent. So this is the combination you can use. You can use multiple stage, all well points. You can use well points and also the deep well together. So, and then this is another method to the deep well system. So the same thing over here, the discharge. The deep depth of excavation is more than 30 to 40 feet, and usually spaced between 20 to 200 feet from center to center, and between 8 inches to 16 inches diameter. And also, so you can see here, the well screen may be used 20 feet long, surrounded by the sound gravel. So again, depending on the situation, what type of soil is there, so you can use that the well screen. Okay. Then the vacuum pump can be used. So here for the fine grained soil, so permeability is less than between 0.10 to the power minus 3 to 10 to the power minus 5 centimeters a second. Necessary to apply suction head, excess head of capillary head, and then also to create a vacuum for the sand filling. So you have a sand filling and then the sealer, and then apply. So again, idea is the same to reduce the water table for the clay type of soil. Then when the clay type of soil, you can use electroosmotic method. So again, in the last class also we mentioned that. So we have 2 electrodes and pass the current, different voltage, and then H plus and H minus, the water will break up. One will go to anode, one will go to cathode. And then mostly the cathode point will be, just well points, and you can just pump the water out from the well points. So, so obviously in this method, the electric current, so direct current generally you required to, between anode and cathode. And as I mentioned, electrode spacing should be 4 to 5 meter. And the potential difference, obviously, of the electrode kept between 40 to 180 volt. And the placement of electrodes is done in such a way that cause movement of water away from the excavation. So you need to choose this, which one should be anode and which one is the cathode. And then obviously cathode side will be the well point. Okay? And thus thereby increase the shear strength of the soil and the stability of the slopes. This is how it looks like. So you see here, this is to the pump over here. This is the well points, is anode, this is cathode, and this is the initial water tables. There should be the voltage difference, and then the water will be going towards the cathode, and then you pump the water out. Okay? So this is again, this is how the how it looks like. U.S. Army Corps of Engineers, so the well point header, and then well point pump. What is the anode probe and cathode probes? How many you need to do? Several of them, and then and then put a the well point obviously to the pump where the cathode, right? So then the velocity of flow towards the cathode. So it depends on this the equation of the Scott 1968. So you can velocity flow, you can find out K minus IC. Her K is not the permeability, is the electroosmotic coefficient of permeability because it's electric gradient. And then also IC is the same like I is the hydraulic gradient, change in head loss divided by the distance. Same thing over here. Electric gradient is the electric potentials divided by the distance between these two electrodes, exactly same. And then these will give you what type of, for the water table reductions, depending on the particle size, what method you need to use. So whether you use the pump, submersible pump, whether you should use the well point system. And if it's a clay type of soil, you have seen that you need to use the electroosmotic method or vacuum consolidation method to find out. So to lower the water table. So in general, design of water table required groundwater dewatering required the size of excavation. So is it now what should be the safe and planned dimension and depth? The soil condition, what type of soil is there at the site, permeability of the soil, unconfined compressive strength of the soil, depth of water to be lowered. So depending on the method, the water table reductions, you can use any method. Stage of well points, number of well points or deep wells. So you need to decide that. The spacing of the well points, how many number of well points, what should be the spacing of the well points. And then also you need to know the pump size. And then also the pipe size, how much is the diameter of the header or riser pipe. So all these things you need to decide to lower the water table or dewatering technique. So here, theoretically, the excavation below the water table necessitates some kind of dewatering technique. So again, low permeability soil when the clay is less than 10 to the power minus 6 centimeter per second. Do not present much problem with seepage because the discharge is generally small. And then if the more than that, so obviously then the dewatering technique is good. So because the problem is, when you have make a borehole, if the permeability is too low, the water cannot come to the well. So you cannot pump the water out. So the permeability is very low. Field control, although it is expensive, dewatering often becomes necessary to underground construction. So as I mentioned, you are constructing basement or water table is too up. So you need to reduce that or underlying pipe installation or anything. So that type of situation, you need to do that, although it is expensive. So dewatering process, I'm not going to go in detail over here. As I mentioned, all these methods are there. So you need to see design method. You need to check what type of pump size we already explained. So you can just read that. Summary of dewatering technique again of initially methods is sump and pumps and ditches. Then the conventional well points, the vacuum well point, deep well point, and electroosmosis and jet equator well point system. So these are the different system, depending on how much is the capacity you want to reduce the water table reduction. So this is a summary of that and what type of soil is applicable. It's a well point dewatering system. Some of the things you can see over here. These are the header pipe, and then the vertical one is the riser. There are several and it can be connected, and then the main pipe is connected to the pump. Okay, so this is how it looks like. You see the pump is there, huge pump. There is a header pipe, and there is a riser. There are several, and there is different spacing. You can just pump the water out. So design parameters we need to check. The most important thing is height of the groundwater above the base excavation is required, and then also the permeability of the soil over there. So if you make a well, if the permeability is high, then the sand and gravel water will go quickly, and then you pump the water out. It's easy well point method. But if the permeability is low, then in that case either use this the vacuum consolidation method, or maybe that, as I mentioned, the electroosmotic method. Okay. So then there are a few things you need to check for every the well points. How much is the area of influence? So this is the equation you can use to calculate. So every well point, how much is the area? So basically, as I mentioned, if you well points, there is a radius of influence. Okay. So how much is the radius of influence? So you can use this equation where Ri is the radius of influence, and then C prime is the for different well, for the single well or for different well points, and then height of the phreatic level. So how much is the initial phreatic level? How much is the drawdown at the end? And then also you need to know how much is the permeability. So now the thing is, it can be arranged in a circular way, or it can be arranged arbitrarily. So and then so what should be how can calculate how much is the discharge? So it's the point P over here. This is that if you know the distance from the different well points, and you can and irregular. So this is the equation you need to use. The first equation. The second one, if the wells are from the pumping well, the point P. So if it is a circular arrangement, then this is the equation you can calculate how much is the discharge. So I'll be solving one problem using this equation. So I'm not going to go in detail here. Deep well system. So this will give you some idea. This is from the Mansour and Kaufman's paper. So basically, how much is the size of the pump, minimum size of the well, how much is the maximum capacity of discharge. So all these things you need to decide. So and this will give you a guideline. Okay. And as I mentioned, the design chart, the well point system, this is the clean. I already mentioned this is from the NAVAC system design chart. This is for the clean stratified gravel. Earlier one is stratified gravel. This is earlier was the homogeneous gravel, sand and gravel. And now this is again, as I mentioned, the same table I mentioned over here. So just for example, if you are designing a deep well system and we have a different well point, so we need to know how much is the equivalent area is going to cover. Okay? So, and then from there, you can find out how many number of wells required, how much is the total quantity of discharge, and then how many number of well is required to complete this dewatering system. So I'll be solving some problem, maybe one from here. And this one is the cutoff wall. So generally we don't use that just dewatering, not dewatering, so this is total cutoff. The sheet piles, that may be diaphragm walls, there may be solid slurry trenches. The second drill seal sapped walls, tremie seals, permeation grouting, and the ground freezing. So these are is complete cutoff water. Okay. Then I just want to talk about a little bit of that preloading one. Now how to improve the get rid of the water basically, and then how to improve the strength of the clay. There are different methods we need to use. One is the preloading or pre-compressions. Okay, so also I'll be using these methods. Do you think I should use first instead of pre-compression? I should talk about consolidation first, and then I'll come back here, or everyone knows consolidation process. I'll go quickly maybe after I explain this pre-compression things. Okay, So preloading is basically, you just put a heap of soil into that particular area, and then, the clay is going to settle because permeability is low because it is going to settle. It takes longer time. When the clay is almost settled, when it's done, then you remove that preload and then put your actual structures. So when you put your actual structures, then there will be a less settlement. There will be no settlements. Okay. So preloading of the soil must include consolidation, which decreases the volume of the voids, resulting in the settlement of the soil surface. And each foot of granular clay deposit, so sometimes the load is coming on the soil is basically 100 pounds per foot square. And sometimes if you put a 30 feet of height of this preload, the foundation load is sometimes 3,000 pounds per foot square. Okay? So it is quite heavy load, and that is suitable for many structures. So that's why people use like a 30 feet and then leave it. Sometimes if the soil is very soft, even 30 foot or 10 feet, just put a soil and then the soil is going to fail. So in that case, you cannot use that the heap of soil. So in that situation, because that heap of load, soil cannot even take that load. So in that case, the vacuum consolidation will be suitable in that situation. So pre-compression, as I mentioned, is simply a place of surcharge fill on the top of the soil that requires consolidation, and just leave it. Once the sufficient consolidation takes place, the fill can remove and construction takes place. Okay? Fill typically 10 to 25 feet thick and produce a settlement to 1 to 3 feet. Okay, most effective in clay type of soil. Again, the consolidation is the expulsion of water from the soil sample, so it takes time. So so most of the time, what you do, you need to put a settlement plate or you need to put a pore pressure transducer. So that will tell you when you need to remove the load. So when the pore pressure transducer, meaning it shows the pore pressure is 0, meaning the consolidation is done. Consolidation is expulsion of water from the soil sample. When the consolidation is done, there is no water pressure. So then they remove the water table. Also, you can measure the settlement plate, find out the settlement below the heap of the soil. So when the settlement is almost constant and stable, then you just remove that load and do your actual consolidation. So advantage of pre-compression is requires only conventional earth moving equipment, just heap the soil. The only thing is where you are going to heap up soil, that much quantity. So any grading contractor can perform this. Long track record for success is very easy method. Okay, you see the Q1 and Q2, so obviously more load, settlement is done. So then the actual structures is going to undergo less settlement. Disadvantages: surcharge fill must be extended at least 10 meters beyond the perimeter of the plant surface, plant construction. So you have to go a little bit wider. Transport of large quantity of soil is required. Sometimes it is not locally available. There is no point. Then the surcharge must remain in place for months or years. That's the delay construction. So when the construction is we don't need the construction to be faster. Just delay construction. So then you just wait, keep that load, and then just leave it for some time, and then see when the consolidation and do it. So sometimes we don't have time, so we need to do the construction faster. So what I need to do, we need to accelerate the rate of consolidation. So that is the different methods. We're going to talk about that using the vertical drain. So you will be either using sand drain or band drain or PVD. So this is what is happening in the settlement. So when you put a surcharge load, obviously with the time, how the sample is going to settle, and that when the final settlement is even more than the design settlement, so that is easy to design your structures. Okay, because whatever the design settlement you are expecting, the settlement after you put your structures is already settled that much. So it's very easy. It's not going to settle anymore. So this is the again the surcharge load for the clay sample over here, and what is happening. So we have that the surcharge load and the final load. How much. So then we can find out how much is this the total pressure, pre-consolidation pressure. How much is the pressure plus surcharge pressure. So most of the time this is easily you can find out that under the surcharge load. how much is the degree of consolidation. So again, you need to go back to the consolidation. So what type of clay is there, whether it is normally consolidated clay, whether it is over consolidated clay, and how much the load you are applying. So whether it is more than pre-consolidation pressure or less than pre-consolidation pressure. So easily you can calculate the settlement. There are different graphs are available, so you can easily find out from here. So this graph, and you can find out also from the degree of consolidation. Again, degree of consolidation is how much is the ultimate consolidation compared to the current state of consolidation. So easily you can calculate that. So from using this equation. Okay. So I'll be solving one problem also using this equation in pre-compression. So again, you need to go back to the time factor and degree of consolidation. So degree of consolidation and time factor, there are several relations there depending on the degree of consolidation and time factor. Then, as I mentioned, that when there are situations when you don't have that the pre-consolidation pre-load, you don't have the enough soil available at the site. So what you need to do the vacuum preloading. So vacuum preloading, so using atmospheric pressure and apply vacuum, and then no need to add heap up soil. So that is the advantage of using this. Okay? So and this method is first introduced by Zellman from German, the German guy, and he utilizes atmospheric pressure to the preload soil. It consists of vertical drain, it consists of horizontal drain, it consists of drainage layer, impervious membrane, and peripheral trenches, and the vacuum pump. So obviously, when you apply vacuum, we need to put that on the top surface. It should be completely sealed, and then apply vacuum, and then atmospheric pressure, and then there should be the peripheral trenches, and then again you pump the water out, basically. And obviously, there is a isotropic consolidation, it's a vacuum drain. So obviously, most of the time, idea of using this vertical drain is most of the time when you apply load for a clay type of soil, the water will go on in the vertical directions. But if you use the vertical drain, the water can go in the radial direction also, in addition to the vertical drain, and thus increase the rate of consolidation. So this is the idea of using vacuum preloading. So what is happening over here in the preload? This is what is the difference between this field preload and the vacuum preload. Field preload is you have to put a heap of soil, right? So we need this much of quantity of soil. The vacuum preload, you see there is no soil. Only thing is you have a sand layer and a little bit of the barrier material to seal it, and then using this atmospheric pressure. And then also there is a trench over here, and then with the membrane, the vacuum preloading is going to occur. Okay? So these are different things. I'm not going to go in detail over here. You can read this. And then the common advantages of vacuum preloading is no extra, as I mentioned, so no extra fill material is needed. Construction times are generally shorter. It requires no heavy machinery. It doesn't require chemical admixtures. Okay, we will talk about more the chemical admixture things later on. So further advantages of this is isotropic consolidation. Again, we are using that eliminate the risk of failure under additional loading to the permanent structures. There is no risk of slope instability beyond the boundaries. Obviously, most of the cases when you use the fill material, sometimes the load is too much. Even that preload soil cannot take it. The soil is very soft. Okay? And it allows controlled rate and magnitude of loading and settlement. Okay? These are the few advantages. And the problem associated with vacuum preloading, obviously there are every method some advantages and disadvantages. To maintain the effective draining system under membrane that expels water, air throughout the whole pumping duration, it is difficult. Keeping a non-water saturated medium below the membrane, also it is difficult. Maintaining an effective level of vacuum. So again, you need to be properly sealed. Maintain the leak-proof system, in particular to pumps or membrane connections. Anchoring and sealing of the system at the periphery, also where the pump is, peripheral drain is there. So we need to, anchoring is required. And then also reducing the lateral seepage towards the vacuum area. So theoretically, it apply around 100 kPa, but practically is 60 to 80 kPa. Okay. So there can be lateral steep drain also, using that lateral steep drain. So to remove the water. So again, this is the example of, as I mentioned, the vacuum and preloading. So obviously over here, we can use both, use the field load plus the vacuum. So over here, you see the vacuum. There is a geotextiles, geomembrane over here, and apply vacuum over there. So we can combine these two methods together, and then also the vertical drain to remove the water. This is again suitability of preloading. It depends on the cost effective. I mean, depending on situations. So vertical drain can be used shorten or time preloading. Again, typically install a depth of 30 meter, vertical depth more than 60 meters or more than 60 meters in some project. Preloading is effective when the loading is higher than the soil pre-consolidation stage. So again, as I mentioned, sometimes even preload, the soil is very soft. It cannot take even the preload. Okay. So this is installation of the sand blanket and the vertical drains. So we'll talk more in the PVD one, but this is the PVD, the vertical drain you can use. I'm just going to go in detail. Seal the membrane, how we can install that monitoring instrument, all this stuff, the vacuum and surcharge. So again, I just want to tell a little bit of this. So here you can see for three different situations. This is like figure B is the conventional surcharge. So basically what is happening into that, the total vertical stress, effective vertical stress, and water pressure. So what is happening over here? And then, so over here, initial conditions, you see the total vertical pressure and water pressures. So again, you need to understand that. So the pore water pressure is EU generally, and then the effective stress is total vertical stress minus the water pressure. So the more effective stress is more, meaning it can take more load, right? So in terms of over here, in terms of vacuum-induced surcharge, you see the water pressure is negative. Okay, the water pressure is negative, so that is good basically. So water pressure is more means what? So the effective stress will be less. So in the soil mechanics, you need to understand that the effective stress is more. Effective stress is the water pressure is more is not good. Okay, the soil, for any type of soil strength is coming from what? For granular type of soil, the friction between the particles, right? Friction between the particles. More friction means more strength. That is for the granular type of sandy type soil. For clay, more strength is made more stickiness, correct? More cohesion. So now the thing is, pore pressure increase, meaning what? So you assume there is a soil particles, another soil particle. The pore pressure means water filled inside the voids of the pore space, right? So now pore pressure increase means what? Water pressure will try to separate these particles. So basically, instead of friction or instead of increasing the strain, is to separate the particles. So suddenly the soil loses its strain. So that's why during the earthquake, what happens? The pore pressure increases. Suddenly, soil loses its strain because there is no contact with the soil particles, and then soil collapse, okay, or foundation collapse. So over here, in case of vacuum surcharge, the total vertical stress remain unchanged, and then the increase in the effective stress due to reduction of the water pressure, and that is the applying negative pressure. Okay, and in case of conventional surcharge, the total stress will increase due to additional load. Okay, thus the effective stress will also increase as well, where the water pressure remains unchanged. Okay, so this is the conventional surcharge and the vacuum surcharge. Vacuum preloading, as I mentioned, these are the different things. These pictures have taken from basically Jihan's book, but mostly I visited in Shanghai, China. So there we really observed all this stuff. How they install this PVD installation of the drainage tubes. It's a huge area, and then the vacuum pump. So all this basically the PVD, and they are not using sand drain, but using this PVD, and then geotextiles, and then also the vacuum preloading. All these things they use in this area. The PVD rigs, it was, you see, it's very, the water surcharge sometimes is very, is difficult. So here view of the project, this one, in Shanghai, as I mentioned, so it's a huge area. So most of the time, what they did over here in this project, so they the dredging material from the sea, and they are just the pump. Ideally, it should be sand, but they pump the clay, and then the slurry and clay water, and then they want to do the construction on that type of area. So we have to do the PVD, we have to do the vacuum pre-consolidation. So you cannot apply the huge surcharge load on the top of the soil because it cannot take that load. So that's they use the PVD and the vacuum consolidation to consolidate the area. Okay. So this is the area, planned area, as I mentioned. So this is how the water is coming out using this PVD and surcharge load and using vacuum. This is a huge area, it looks like. So these are the different pumps you see, and then also the below there is a vacuum geomembrane, and then a little bit of surcharge. And then also this is how it looks like, the vacuum preloading, and also what is the connections, and then also you see the large vacuum pump to release the water. This is the vacuum preloading. We'll be talking about more in detail. So basically the PVD is basically there is a high density polyethylene type of material at the core, and on the top there is a geosynthetic material, and then so that only the water can pass through, and then and it will no soil can pass through that. Okay, and then it will go the vertical directions. Okay, so that's the idea of vertical preloading. So these are the different connections they used, and then top is the PVD, how they're connected. So this is the old one. Earlier they used the older system. Now have a newer system like that. They used more efficient in connection a few drains and to use. I mean, it is not easy. It's a very simple process, but a huge area, and then installation of PVD, and then connecting it, and then apply vacuum pressure. That is a bit challenging because the soil is so soft. Okay. Then the vacuum preloading also, as I mentioned over here, this is how it looks like. And then over here, this is the how obviously when the consolidation is done, then you need to check how the strength increased. Then you need to do some tests at the site, and then you can determine how much the strength has been improved. Okay. So these are mostly the vacuum preloading and then PVD stuff. Okay. This is another air injection hose. Sometimes you use for the test section, vacuum preloading. It's much more detailed, but I'm not going to go in details over here. And then the electroosmotic I mentioned already, vacuum preloading. Also, they use that electric current, and easily you can calculate that. I'm not again. So they use that electroosmosis, but they use the electrokinetic. They use the electrokinetic geosynthetic material. So geosynthetic is there is an electric piezoelectric piezometer are installed, the conductive polymer. So conductive polymer is installed in the PVD itself. So and then the electro. So basically, you can say this one is electroconductive electroosmosis with this conductive polymer. Okay, so we call it EKG. A little bit different electroosmosis method. This is how they do at the site. The vacuum preloading, including this one electrokinetic geomembrane. So, and then the connection between the pipe and the geomembrane. So the PVD, how they're connected to the vacuum tube, and then next to PVD. So all these thing connections are there. How it looks like, the drainage tubes. A lot of pictures. Again, these are the pictures from the Shanghai, China. This is how they install the membranes. This is a huge area. So how the installation of the membrane. So it should be impermeable membrane. So that apply vacuum. This is how it looks like, the overall, and then the perimeter trenches. and then you can just use the pump to get rid of the water. Okay. This is how it looks like the settlement with time. You need to use that, as I mentioned, so like the sensor is attached to that electrokinetic in geomembrane. So, and then find out that they compared with the normal one, and then also use different types of the piezoelectric with the sensor. Okay, and then they mentioned that although these sensors are is very recently new, so people are and they prove that okay, this is much better. The settlement is much better than the conventional one. Okay, so I just any questions from this? So we have how much time? So
Sir, just a minute. Actually, I just request you to this the first slide of vacuum preloading. So can you
okay,
explain that? The first slide of vacuum preloading,
first slide.
in which the entire process is there's a
Yeah.
schematic diagram.
Okay.
That one, sir. In which it's clearly
Yeah.
shown the trenches, etc.
Yeah. Yeah.
I guess it is slide number 62 or 63. I guess
62.
I think so. I'm
This
not
one?
sure.
You're
Yes,
talking
this
this
one.
one?
Yes, sir.
Okay.
This one. Yes, sir.
Uh-huh.
Yes, sir.
This is the schematic diagram, but the pictures you have seen in the Shanghai, as I mentioned, so no, this is it is difficult to control. I mean, this is it seems like okay, you apply the vacuum, you apply the sealing, even the sealing using geomembrane, and then how to anchor at this the peripheral side on the side. It is not easy job. You know, you need to always you need to losing the vacuum. You know, and then also the clogging and then PVD. You know, so a lot of things. So what is the question?
So actually, this vacuum, how actually this was what I was a bit like how they are able to maintain that vacuum in this
Yeah,
particular.
that's the one. You know, you
Yes,
cannot maintain that. It is difficult. You know,
yes,
as I mentioned. So when I visited that the Shanghai, in the side there is a constant, continuously they are monitoring, and then obviously they will be losing some. You know, every time it is difficult to maintain the vacuum pressure, and because it depends on how you seal it, and then sometimes the laying of geomembrane. Sometimes you know if there is any leak in geomembrane while in a huge area, it is very difficult, and sometimes you have to anchor it, right? And then also how they are you have seen a lot of connections, you know, the PVD, and then in the like a riser pipe or header pipe, that type of connections, there are different types. How, and then there are multiple of these, you know. So it is not easy task, but you know, and these pictures is basically that ideal situation, but in real life it is different, you know. I mean, if you see that the pictures, all this the picture I have
yes, sir,
shown,
yes, sir.
yeah,
Mhm.
that one again, it is not easy. On the site itself, I have seen there are 2, 3 site office, and all the time they are monitoring the pump capacity of the pump, which one is even for uh, you know the construction site. They have huge generator. You know there is no electric supply there, so all this time is a very expensive process. And
Agreed,
as I
sir.
mentioned, yeah. And then
Yes,
also,
sir.
as I mentioned, because they use vacuum, because the soil is so soft, you cannot put a heap of soil and then keep it for some time. It's going to
Preloading, yes.
fail. Yeah.
Okay. Thank you so much, sir. Thank you so much.
All right. So, any other question? So this is most of the notes I've taken from this Jihan's book, you know, uh, and some other books also. All right. So if it is not no questions, then I can just continue again. The next
Yes, sir.
topic is yes.
Sir, there is one question in the chat box. I'll read, sir.
Okay.
How commonly is electro-osmosis used for dewatering?
Again, if it is normally, you know, when we cannot use the oil point method, right? So when it's pure clay and if there is no choice, so then you can use it, you know. you can use that. Also, sometimes electrokinetic method, the same thing you can use for not only dewatering. So you can use that method basically for the removal of contaminant from the clay soil also. Okay. So again, when the other method is not suitable, like a well point is easy, or when you then you can use that. Then obviously we need to have the electric gradient, right? So you need to pass the voltage and direct current, and then you have to have that well point system. One will go to cathode, one will go to anode. Okay. Does it make sense? So generally we don't use that, but if it is, we need to. And if it is a pure clay, permeability is really low. The water cannot flow at its own. So in that situation. All right.
I think that there is no more questions.
Okay.
So I just want to understand these PVDs, prefabricated vertical drains. Is there any specific design
yes,
for
yes.
different
I'm going to
soils?
talk about. I'm going to talk about that in the next section. The PVD and the sand drain. I'm going to talk about that. And
okay, yeah. Thanks.
Okay. So now the next topic is the consolidation. Do you think that I should explain the consolidation, or I just go quickly? Just to quick refresh, or whatever we say,
So better refresh, sir.
Okay. So
But if time permits, of course.
Yeah, I'll just go quickly because I know everyone knows consolidation. Just to go quickly and then. Can you see now?
Yes, sir, it's visible.
So what you can see?
This Tarjagi 1D consolidation theory slide.
Okay. Again, you can see now consolidation, correct?
Yes, sir, you can put it in the full screen mode. It is in the slide mode at the moment.
Oh, really? I
Yes.
put it in full screen mode. I can see full screen here. Maybe is it, can I don't know whether the other slide is still there or not.
No, sir, it is not moving right now. Only the 40th number page is showing.
Oh, okay. So I think I just stop share then. Okay, just a minute. Sorry about that. What can you see now?
Yeah, it's okay now, sir. Yeah, this is the consolidation page is open.
Okay. So consolidation, again, I'm not going to go in detail. So this is because this topic is mentioned consolidation of soft soil. So consolidation of clay is basically consolidation and expulsion of water from the soil sample. So when you apply load, what is happening in the saturated soil? So all the load is taken by the water, and then you transfer to the soil, and then you need to keep it. It is a time-dependent phenomena, and then it is not quick, because the probability is low. And so obviously, I'm not going into details over here. So obviously, the change in shape, distortion, and compressions, all this stuff. Okay. So sometimes when I'm not going to go into details. So when you do the consolidation, so basically, you need to, on the consolidation test, you can find out the different parameters to find out the settlement idea. The idea of how to calculate the settlement, right? So we can find out the immediate settlement, primary consolidation settlement, and secondary consolidation settlement. So granular soil, what is happening immediately? The soil is really settlement is immediate. But it's a clay type soil. That with time, the settlement is it takes time, and then settlement is going to take place. Again, you need to go that what is the pore pressure. I'm going to go here. So what is happening over here for any consolidation, just for example, at certain point, if you apply a load, the pore pressure is decreasing and the effective stress is increasing over here. So you see the effective stress increase when you can take more load. So as I mentioned, the consolidation is the expansion of water from the soil samples. So this is the spinning analogy you know already, so I'm not going to go in detail. So most of the time, if it's a clay soil is there, so if you apply load, you need to find out how much is the settlement of the clay layer. So it depends on the permeability of the clay, and you need to know the properties of the consolidation test. So from there, you can find out the MV, you can find out AV, you can find out CV, you can find out compression index. From there, you can find out the settlement, basically. So again, this is what is happening over there with time, the total stress, initial time at no time, all the load is taken by this pore water, and then with time, all the pore water is gone. The effective stress is equal to 0, at time is equal to 0. Then what is happening over here? So basically, the clay layer, the clay is sandwiched between two sand layers. Load is coming. So total stress, water pressure is decreasing, and then the effective stress is total stress minus water pressure. It looks like this. Okay. So at the center is different, and at the side is different, right? The effective stress. So most of the cases, sometimes we assume uniform. Sometimes we assume that when the load is coming, it is like a not triangular, but like a more on the top and then a lower at the ground, at the bottom part. Okay. This is at time is equal to infinite. So obviously the total stress and the pore pressure, all the pore has gone out, and then the effective stress is equal to total stress. Okay. So so this is one-dimensional consolidation. So obviously most of the time when you do consolidation is one-dimensional. So basically when water is going only in the vertical direction. This is the Rizaghi's theory. And then in real life, you don't know what type of soil is there. So, if there is a clay layer and there is a sand layer, at bottom there is a gravel or impermeable rock. So water can go only in the vertical directions. So this is one-way drainage. If there is a clay layer and there is a top layer, impermeable sand or gravel at the bottom and top. So then when the apply load, the water can go on the both directions. So that is basically, you can easily calculate the one-way or two-way drainage. And the average strain you can calculate. So again, how much is the height of the soils, how much is the strain, the change in height divided by original height. And there are relations with that, with the void ratio. You can calculate the settlements, from there. I'm just going to go. So here, this is the relation. So change in height by original height, change in void ratio by 1 plus E naught. So if you know how much is the settlement, consolidation settlement, you can easily calculate. If you know the original thickness of the clay, if you know with the application of the load, how much is the change in the void ratio, you can get it from the E log P graph. And then if you know the initial void ratio is that, so you can easily calculate. There are several equations you can use to calculate. So from this consolidation test, you can find out the coefficient of compressibility, that is change in the void ratio by changing the pressure. So again, when you increase the pressure, void ratio is decreasing. That's why the change in the pressure void ratio is negative. Then coefficient of volume compressibility. So we can calculate. So then we can find coefficient of volume compressibility is change in volumetric strain divided by how much is the change in the pressure. So you can calculate that volume compressibility from there. Then Rizaghi's theory again. There are some assumptions made in Rizaghi's theory that the soil is 100% saturated, should be homogeneous, Darcy's law valid. All this assumption made. Soil and grains are incompressible. That is not true. Then the compression or flow rate, all these things you need to know the assumption made. And the sample is laterally confined, but that is also not true in real life, because in the lab test, the sample is laterally confined. So the consolidation test, again, I'm not going to go in details. It's a circular ring, and then you apply a load. So the load increment ratio is 1. So when you put a load, any load, so just for example, 1 kg per centimeter square, just leave it there for 24 hours, and then take the reading with time versus settlement. And then you go next day, you increase the load, just double. If it is 1 kg, then you put 2 kg per centimeter square, and then take the reading again. And then next day you come, so you just go up to, just increase the load increment ratio as a double, and then keep it for 7 days or 8 days, and then the loading and then unloading. Then from there, ultimately you will get a graph like a E-log P graph. And then from the E-log P graph, you can find out the slope of this line. That is the so there are two types, again, consolidations. One is the fixed ring, another is the floating ring. So most of the time in consolidation, we use the fixed ring method, the bottom one. Sometimes you can use the floating ring also. So normally consolidated clay, so again, the consolidation of clay, when you talk about, so you need to know what is normally consolidated clay, what is over consolidated clay. Normally consolidated clay is the clay, the soil has never experienced the stress more than the current stress. Over-consolidated clay is the soil has already experienced the stress more than the current stress. The behavior will be different. And then the settlement equation, so is also will be different. So this is like a E-log P graph. So it is a loading and then unloading and then again reloading. So this is how it looks like. This is the graph you can find out from pre-consolidation pressure. So from the E-log P graph, you can draw a horizontal line at the maximum point of curvature, draw a tangent from the bottom, and then you see the tangent from A, and then make this angle. You divide that angle, and then draw a tangent from the bottom part, and then see what is that pressure. That is the pre-consolidation pressure. That's why you can easily find out. That's why the soil has memory, so it can really find out how much is the stress history. It was there, how much is the soil stress. So I'm not going to go in detail here. There are different relations between this compression index and recompression index. So there are several relations that are available. So we can find out for the normally consolidation pressure. So here, if you slope up that line is the compression index. This is decompression index or swelling index. There are several relations that are available. As I mentioned, pre-consolidation pressure. So I'm not going to go here. There are over-consolidation ratio. Also, you need to know how much is the pre-consolidation pressure divided by how much is the initial stress. So you can easily find out from there how much the soil is over-consolidated. Most of the time, the over-consolidation ratio is 1. So meaning that soil is normally consolidated soil. And the settlement calculation, this is the most important. Then later on, we will talk about that. The settlement. So settlement, you can, if you know the MV, that is the volume coefficient of volume compressibility, then you know the pressure change. You know the height of the clay. You can find the settlement. You can calculate from the change in void ratio by original void ratio. And if you know the height, then you can calculate the settlement. There are 3 types of the settlement. You can calculate the compression index. You can calculate from there the slope of these margin compression lines. And there are some relation, as I mentioned, the compression index. There are some relations are there with that recompression index or swelling index with the compression index when the data is not available. You can use this. And this is the settlement calculations when you have the pre-consolidation pressure and additional load is more than pre-consolidation pressure. So we can use this. So just behave like a normally consolidated clay. This is delta S is equal to Cc times H by 1 plus C naught. Initial pressure P naught. How much is the change in pressure divided by P naught? Change in pressure is you can calculate using several methods. Either use 2:1 method or Boussinesq equation or equivalent point load method, or you can use M&M method or M1N method or Newmax charts. There are several methods to calculate how much the additional load is coming because of this additional surcharge load. And then you can find out the settlement. So this is normally consolidated clay. If it is highly over consolidated clay, equation is same. Only the Cc is now replaced with Cr. And then if the soil is slightly over consolidated clay, then you can use this equation over here at the bottom. So there, the pre-consolidation pressure is important there. You need to use that. So this is all the equation as I mentioned, depending on the initial stress and pre-consolidation pressures. This is the pre-consolidation pressure. So you can use the settlement equations depending on whether the pre-consolidation pressure is more than the, with the surcharge load. So all 3 equations can be used to calculate the settlement. Okay. I'm not going to go in detail over here. And then again, for the consolidation theory, so this is the theoretical equation of this consolidation, du by dt. The change in the pore of pressure with time is equal to how much is the coefficient of consolidation, and du by dt, that is the d square u by dj square. Okay. So the CV is the coefficient of consolidation. CV is equal to k divided by mv by gamma w. Again, you can easily calculate that CV. And there are several, how to calculate the CV. There are two methods, again, the Casagrande method and Taylor's method. So, and there are relations also between U and time, that the time period. So I'm just going to go just one case over here. This Casagrande method, you can calculate how much the value of CV over here. So CV is equal to 0.197. How much is the degree of drainage? Only thing is the degree of drainage is depending on what type of, is it one way or two way. And then another method is the square root of time, is the Taylor's method. So we can calculate. So here you can find out how much is the D90. So 90% consolidation CV is equal to 0.848 height of drainage times T90. So you can easily calculate that. And then also other method, there are early stage method, hyperbola method. So you can use that also for how to find out the CV. Okay, I think so for the settlement, you can calculate elastic settlement, primary consolidation settlement. In real life, you will not get your clay. If you have granular type of soil, you can calculate for the elastic settlement method. There is several equations you can use, and then you can use for primary consolidation settlement. You can use for secondary consolidation settlement or creep, or if there is highly organic soil, you can use the tertiary consolidation also to find out the total settlement. So anyway, so this is, I just go very quick about this consolidation. Okay, so I'm just I just want to stop this sharing this, and then I'm just going to share that. Vertical drain practice. Just a minute.
So I think, sir, we will end the session, sir, right now.
Okay, you think that, okay? And so that will be easy even. So after what time I should do that actually? It's 9:50, right?